We'll start by finishing off the example that we started last time, where we modeled a system of components, which was exemplified in this case by a digital circuit with 3 gates. We will finish this example to discuss the problem that we ended up with last time, and then we will go ahead and cover more cases for modeling. We have basically maybe 4 or 5 more cases. We'll do them more briefly, though, as we're now starting to pick up on the various techniques. And then towards the end, we will talk about some related issues to modeling. One of them, for example, is how to deal with the problem of having too many parents per node in a Bayesian network, and so on. All right, so we'll resume our example about circuits. And if you remember, what we did last time was we had this particular circuit, and we modeled it using this particular Bayesian network, and the structure was basically generated in somewhat of a systematic way. A gate here represents or generates this fragment, this gate generates this fragment, and so on, right? Where we had a particular test vector. In this particular case, the input was high, both of them, which according to this circuit, and if it was functioning normally, we would expect the output to be high as well. But we actually got a low output indicating a problem. And we asserted this as evidence and then computed the map over the health mode variables x, y, z to try to find out what's going on. And that what we got is 2 most likely instantiations of these variables. One blaming the y component, and the other actually blaming the z component. And that basically leads to an ambiguity of what particular component is responsible. And what we ended up with last time was, how do we resolve this ambiguity? So there were suggestions that maybe we can probe some of the internal wires. And the other suggestion that we ended up with is perhaps we can try another test vector, right? So we try another input and output and take this test vector together with the other one, put them together, and maybe that will help us isolate the fault. Again, if you remember, the hint I ended up with is, if we want to integrate 2 test vectors, then we need our model to actually have enough variables to capture that, right? The first test vector is an input-output. The second test vector is an input-output. And what basically that leads to is we need these basically additional variables in our model. So if we had A, B, and E as the input and output, we now will introduce A prime, B prime, and E prime to capture the values of the second test vector. And as you will see, we will also introduce these additional variables, C prime and D prime, as intermediary variables. But basically, you can think of it as we need 2 versions of the circuit. One during the first test vector and the other during the second test vector. And let's see how this is going to look like. Here's our new model. So look at it carefully and see what's going on here. So we have almost 2 replicas of the Bayesian network, right? So this is the original guy we had. There is the inputs A and B. There is the circuit output E. Here's are the intermediary variables C and D, and then the health mode X, Y, and Z, right? So this is what we used initially. So when you told me that A and B were high and E was low, I asserted that as evidence and computed a map over that. Now, when you give me another test vector, which in this case, both inputs are low, the output is still low as well, look what we did. We had this new version of the circuit, or this replica or instance, where every variable is A prime. Think of this as during the time of the first test vector, and this is during the time of the second test vector, so time 1 and time 2, right? So it's pretty much the same structure, but look what's interesting here. Even though we created 2 instances of the wires, right, for the different time points, the health modes are shared. Now, what does that mean? That means that tacitly, we're assuming that the health of a component does not change over time. That whatever health a component had during the first test vector, it's exactly the same during the second test vector. Now, that's a modeling assumption. That may not be the case. It's possible that a component may be okay when I tried the circuit first, but by the time I tried the second test vector, maybe one of the components flipped its state. That would not be okay in that case, right? Because again, this is assuming that it is the health of the components remain constant across the two test vectors. All right, so we're going to see now how we can relax that assumption. But if we go ahead with this model actually and assert both test vectors, look what happened in this case. We get only one map. Given the combination of evidence here, it's Z. It's, Y is no longer a possibility. And in fact, the probability of this particular instantiation is pretty high. It's 97.5%. Right? Now, if you have yet a third test vector, you just have yet another slice. Right? So you have 3 slices. So now, how are we going to deal with the situation where it's possible that the health of a component may change over time? We need to have a primed version of X, Y, Z to represent the health mode during the first test vector, the health mode during the second test vector. But now we have to also do one more thing because they are not unrelated, right? Exactly. So you'll see that we will need something that people call a persistence model. Here's how it's going to look. All we did here is look at X. Now we have X prime. So we separated these. And now we have Y and we have Y prime. And similarly for Z. But look what we did also. The parent of X prime is X, which basically saying that the health mode at time 2 is basically caused by its health at time 1. And when we do this, then we need more information now in the model. Right? Realize in the previous version, we didn't have to add any more information. Our CPTs were just as is from the single slice version. If we use this particular one, now we need CPTs for the X prime and the Y prime and Z prime. And what are these look like? They look like this. They're called persistent models because they're effectively telling us, look at this guy here. What is the probability that the X component would remain okay during the second test? Or this guy, what is the probability that it will flip from being okay to being faulty? And this is flipping from faulty to okay and so on, right? So again, as I said, this is called the persistence model. And this is now allowing, for example, for the possibility of temporary faults or intermittent faults. Something just goes wrong for a little bit and then it's okay again. So you need more information for this. Now, the creature that we now have is actually pretty interesting because it's exemplary of a broader class of Bayesian networks known as dynamic Bayesian networks. All right? What you're seeing here is a common template. That is, I have a set of variables and their values change over time. And then I have a network that's made of slices or temporal slices. In this case, there's only 2 of them, right? This guy and that guy is almost the same, right? Pretty much the same. The only difference is, for this slice, some of the variables have their parents coming from the previous slice, right? And now we only have 2 slices here. You could have more. When you have a structure like this, as I said, it's called a dynamic Bayesian network or a DBN. In principle, when people say DBN, they assume that a particular slice at time t depends only on the slice at time t minus 1. But in principle, you can talk about more general dynamic Bayesian networks in which dependence could go further in the past. Now, does this remind you of anything, of any other model we did before? Exactly. In fact, the hidden Markov model is a very simple type of a dynamic Bayesian network, right? What's in a hidden Markov model? In every slice, we only have 2 variables. The simple state variable and the sensor variable. That's basically what we want to say about this particular example. Now, we will look at another example next, which also involves synthesis. That is, we will build a Bayesian network by synthesizing it from another class of systems. The one we're going to do next, let me see if we have this slide. Yes, here it is. This is a classical problem from reliability engineering, and where you have what people call reliability block diagrams that are meant to capture the dependence of a system on its components. So the idea here is to say something like, I have a computer system, it has these components, and they do have their own reliabilities, and I want to be able to compute the overall reliability of the system. So for example, you look here and it says at 1,000 days since initial operation, reliability of the power supply is this, the fan is that, processor is this, and so on. And then we're asked, what is the overall system reliability at 100 days since operation, right? We'll interpret this in just a second. But just before I go into this example, let me tell you more about it and something else we're going to do later on genetic linkage analysis. So we're doing these examples. The main reason is to practice modeling and use them as a context to communicate some of the modeling tricks that come up often, even beyond these examples. That's the main purpose. Particularly that in these examples, the technique is that of synthesis, that I have some other type of information and I can eventually automatically generate the Bayesian networks from those. It's very important practically. But the other thing I should mention here before we move on, and also in genetic linkage analysis, both of these problems already exist in their own literatures, and there are people who have dedicated themselves to solving them, right? So this comes from a book on reliability engineering, and there are algorithms for doing the exact same thing that we're going to do now, that were developed by mechanical engineers and reliability engineers. Same thing for genetic linkage analysis. We're going to look at a problem that's been around for decades. But here's the interesting thing. When people develop these algorithms, they develop them specific to these problems. When we map them to Bayesian network inference, then we will be able to have an alternative approach to these problems, which is based on the general algorithms we have to Bayesian networks. So now you have two competing things, right? Dedicated algorithms that were developed for these problems, and then general purpose algorithms for Bayesian networks that I immediately get when I transform these. You would expect that the dedicated algorithms will do better. In fact, not necessarily so. One of the surprises, for example, when we do a genetic linkage analysis later, that when people did this, they were able to obtain results from Bayesian network inference that were better than some of the dedicated ones developed for a very long time in that literature, which is pretty interesting. In fact, I'll tell you more about this later. For genetic linkage analysis, for example, we had one of our students actually in my group dedicate his thesis to these problems at some point. So, and this keeps recurring. This situation where you develop something general purpose like a SAT solver, and then use it to solve specialized problems, and you tend to get better results than some of the more dedicated algorithms. It's not an uncommon situation these days. All right, so let's move on. First thing is we need to interpret this reliability block diagram, and here we're using the simplest type of these. There are more sophisticated versions, but the idea is this. The idea is each block here, think of it as a subsystem. So this guy is a subsystem that says, for it to be available, I need the block, the processor, to be available, and I need one of the subsystems feeding into it to be available. So effectively, this is saying I need the processor and one of the fans. You can think of fan 1 as another subsystem. So for this subsystem to be available, I need the fan and the power supply. Right? If you look at this guy, this says I need the hard drive and one of these subsystems. So the interpretation here is if there are multiple edges going into a block, then it's an OR, right? One of the subsystems feeding into that. Now that's the simplest interpretation of these things. There are more sophisticated versions where you could do things like I need 2 out of K and so on, but we're just doing this particular one. What we need is to build a Bayesian network that corresponds to this case and use it to compute the overall reliability of the system. And here's how we're going to do it. And now what you're seeing is something that we've already seen in the previous example, and it would actually recur. where you would look at part of the system you're trying to model. In this case, we have the notion of a block and two subsystems feeding into it, and then see how do you model that fragment into a Bayesian network. And this is how it looks. I introduce a node to represent the availability of the block, right? And then I have an AND node. Think of it as a logical AND node that says, for this system to be available, I need the block to be available and the following to be available. And what is this? This is an OR that says, I need this subsystem to be available or that subsystem to be available. So now we have, you can think of this as a Bayesian network fragment. Now recursively, I have to fill this and I have to fill that, right? And then we just paste this together to produce the overall system. Look what we get in this particular case. Here's how it looks. There are three types of nodes in this Bayesian network. There are these guys, the roots, which represents the availability of single components, right? Processor is available, fan 1 is available, power supply, and so on, hard drive. And then I have these nodes, which represent logical ANDs. They're going to be true and false. So this is true if and only if both of these guys are available, right? And then I have the OR, which is true if and only if both one of these is true, and so on. Actually, this guy here is an AND node, representing the whole system, which says the system is available or true if and only if this is true and that is available, right? That's basically the overall network structure. Now, if you look at the CPTs, there are three types, right? There is the CPTs for these guys, and there is the CPTs for the A variables and for the O variables. And as you'll see, they're pretty straightforward. For the roots, those represent the availability of individual components. We have that information from the problem statement. For example, this is the power supply, and the probability that it's available is 99% at 1,000 days. You realize in the CPTs I'm going to show you now, I'm only going to show the independent rows, right? So in this case, you'll have also another row that says not available, but that's just 1%, 1 minus 99. Now, for the AND gates, as we know by now, there's going to be 0 and 1, right? So this is basically saying I need both of these guys to be available. That's 1. Otherwise, it's 0. And I have something similar for the OR nodes, and that's basically it. So it's pretty simple to synthesize this Bayesian network from a reliability block diagram in this case. And here we go and compute the marginal over the S variable representing the whole system, and we get a 95.9%. That's basically the overall reliability of the system. Interestingly enough, suppose, this is a common query, you're not happy with this reliability. This is, what can I do to make the system at least 96.5 reliable? And that's where you use sensitivity analysis, right? Because the reliabilities of the individual components are just parameters in the Bayesian network. And I'm doing single parameter sensitivity analysis. You get 3 possibilities in this case. You can improve the reliability of the hard drive, the power supply, or either of the fans. We'll do it. Now, if you get a little bit more ambitious and say, no, I want it actually to be 97% availability, then the set of possibilities narrow down. And now you're told the only thing you can do here is just the hard drive. Remember, we're doing single parameter sensitivity analysis. That means you can only change one component. So only the hard drive will bring this up to 97%. Now you get a little bit even more ambitious and say I want it to be 98%, and hard luck, nothing will do it in this case. Changing one particular component will not do this, but possibly multiple components can do that. Now you can also use this, now we've built the system, you can use it to do diagnosis as well, right? So if the system is not functioning at that particular day, you go ahead and assert the evidence on S, right? That S is not functioning, and you can compute a map in that particular case, and what you get is this particular instantiation. So it's basically blaming the hard drive in this particular case. If you use the map tool in Samaya, for example, it will actually give you more, not just the top instantiation. It may give you the other ones as well. And here you see an example of some of the further explanations that are coming up with lower probability. All right, so you really get, once you've got this model, you can do quite a lot of things. Let me show you one more thing you can do here, which is basically pushing further on an observation we did before, and that is how you can incorporate non-traditional evidence through modeling by adding auxiliary variables. All right, and then we would close this particular example. So suppose someone comes to you and says, for some reason, I know that it is not possible for the first fan to be operating concurrently with the first processor, right? So you have this particular constraints. First fan and first processor cannot be both available at the same time. And then you want to do your computations under this particular piece of information. So that's, you can think of that as evidence. The evidence is this particular thing, right? This is a variable instantiation. F1 is available, P1 is available, and I'm saying no, they cannot be the same. So in fact, this is the same as saying F1 not available or P1 not available, right? It's disjunction. It's no longer simple evidence of the type, I know the value of this variable and I know the value of that variable. So what do I do in this case? How do I handle this? We've done something like this before. We add an auxiliary variable, right? And this variable, we'll call it C, and basically, we call this variable C, and it will have these as its parents, and you set the CPT for it as expected, right? If they're both available, that's a 0. Otherwise, if one of them is not available, that's a 1, and so on. And this is where it appears. And basically assert this now and do your computations and so on. Let's say one more thing about this example and move on. In your book, there is a section on the computation of these reliabilities, which I alluded to before from the previous example. Because as I mentioned, there is a field that's dedicated to this. And in this particular case, one of the things that get used is what's known as life distributions. These are distributions that show you the health of the component as a function of time. And one of the common thing is, as I said, this is known as the life distribution, which is basically the exponential distribution. It looks like this. And you can see it is a function of time, and lambda is a parameter which represents the number of failures per unit time. So, lambda is different for different components. So here's two life distributions in this particular case for different lambdas, and you can see how we start at 1 when the component is born, and then as time passes, the probability drops down to a different rate depending on what lambda. So you can read more about this in your book. There's some discussion about how you get these and what's the underlying PDFs and so on, but I just want to give you a sense. Any questions about that? Because we're going to move now to another application. Yes. Oh, so what SAM-IM does is it has two types of sensitivity. There is the single parameter sensitivity, and there is a multiple parameter sensitivity as long as all of the parameters belong to the same CPT, right? Multiple parameters, but within the same CPT. The third level is multiple parameters across CPTs. Now, what's the difference? The difference really is computational, right? So it turns out that if you do sensitivity analysis on parameters within the same CPT, it's still well behaved. We'll see that towards the end when we look at it, how it works computationally. It's actually, you'll see it's beautiful because, and it's not what you expect. We will look at some point at an interpretation of these graphical models, including Bayesian networks, as polynomials. We will algebraically characterize the distributions and do all of this work algebraically on these polynomials, partial derivatives and this and that. Math is very nice and simple. But I think what you're talking about, maybe even doing some tricks by adding some auxiliary variables to tie certain things, yeah, possible. Actually, that's a curious idea. Try it out. I'd be curious to see what happens. Now, you have to realize where you may get the hit is the following. And you'll get a better sense of this next lecture when we start talking about inference. You say, wait a minute, so how did I get away with this. You're telling me that if I do sensitivity analysis across different CPTs, that's a harder problem, but now I just put an additional node and connected them and I reduce it to the first. So where's the magic? The magic is by adding the auxiliary node and tying it, and depending on which two things you tied, you created a structure that's more complex. And that's how you may be getting the hit. Doing inference on the new guy is not as simple as doing inference on the previous guy. And we'll quantify this next time. We will look at a parameter that measures the connectivity of a network, and we use that parameter to talk about the complexity of inference. All right, very good. We're going to talk about one more example now, which is from the subject of coding, which is also very well established subjects. You can take more than one course on this subject. EE offers courses. And it's an important subject in this context for a number of reasons, as you'll see later. First, there is, of course, some modeling things that we have to talk, but there's also some historical connection between some of the developments in this area and some of the ones in approximate inference on probabilistic graphical model, which I'll hint at towards the end. There was a game changer, actually, based on this connection that happened in the late 90s. So here's how this problem goes. You basically have a channel, and you have some bits that you are sending across this channel. In this particular case, we're assuming that we have 4 bits, U1 through U4, on and off. The channel is noisy, so when you send the bits over the channel, you get them distorted at the other end, right? In this case, we're assuming a very simple noise model. We'll improve it and make it more realistic in a little bit, where there is a 1% chance that if you put a bit on one end, it would flip when it gets to the other end, right? And the problem is pretty simple. I tell you, here's what I received at this end. What is the most likely thing that was sent, right? Because what I'm receiving is not the exact thing, right? It is the bits with some of them having flipped. This is basically a very important problem. And if you look at the way this is typically done, you want to try to improve your ability to recover the original bits. And the way this is done by adding redundant bits before sending out the message. And in this case, we're going to assume, again, a simple type of coding scheme where we're going to add 3 redundant bits, x1, x2, and x3, which are computed by XORing some of the original bits. So x1 is the XOR of u1, u3, x2 is the XOR of u2 and u4, and similarly for x3. There are other coding schemes. We're going to mention a couple of them later as well. So again, the idea is, instead of sending the original 4, I'll send the 4 plus 3. Right? So you receive a 7, and from that 7, you try to recover. Again, the point here is then I'm probably going to be more robust. Just to be clear on terminology in this particular case, this is channel coding terminology. The U1 through U4 are called information bits. These guys are called the redundant bits. When I put them together, I get the code word, or what people call the channel input. And then U1 through U7, Y1 through Y7 are the channel output, right? So what are the evidence variables in this case? The Y1 through Y7, right? And the query variables are the U1 through U4. Well, you may consider X1 through X3 as well, and so on. Okay, so let's look at the structure in this case. It's pretty simple. And what you would expect by now, I guess we should do this comfortably. You have the information bits here, and then you've got these redundant bits, and look at each one of them. Just the parents are the 2 guys from which I compute, right? And now I have all of these guys, which are basically the channel output. There are 3 types of CPTs in this case, right? For these guys, for those, and for this guy. For the x1 through x3, that's straightforward, right? Because they're just XORs, correct? So that's a deterministic CPT 0, 1 trivial. These guys depend on the noise model that I have. In this case, we had a very simple noise model, which said the bit will flip with probability 1%. Okay, we're going to do something more realistic in a little bit. And these guys here, we have no choice. We're going to just assume that we have a uniform distribution on the messages sent. Right? Done. Really, it's simple. This is the one for the redundant bits, straightforward from the XOR semantics. This is the one for the noise, right? Again, straightforward. And this is what we're going to assume in this particular case, right? Now, there's two things we're going to discuss on this particular simple coding scheme, which are, again, of general importance beyond this model. And then we will talk about variations, more sophisticated, more realistic coding network, and then we'll go to something else. So the first topic is, how do I query this guy, right? When you give me the evidence, you say, here's the output, channel output, here's what I received, here's the bit, 7-bit vector, and I want to get these guys. What query should I pose? Now you know a bunch of queries, right? What query should I use in this case to do this guy? Map. So I will compute the map on U1 through U4, right? Sounds the right thing to do. Is there anything else that I could do in this case? I could go to each guy and compute the posterior marginal, right? And then pick the state that is most likely, correct? Now, we said before that these are not the same things, right? You don't expect to get the same answer. And in a sense, it looks like you would prefer the map in this case. It seems to make more sense, right? But actually, people tend to use the posterior marginal instead of map in this particular case. Let's see why is that the case, all right? It depends on what thing you're trying to optimize. Look what's going on here. We're trying to evaluate a system like this, which we're going to call a decoder. So what's going on here is you give it, this is the decoder where you give it this as an output. So this is what I received, and it comes back and it gives you that, right? And here's how we're going to check it out. I'm going to do a simulation. I'm going to generate some input, channel input alpha. I will send it across the channel. I'll get the noisy version, beta, right? I give it to the decoder, and the decoder comes back and says, I recovered it to gamma, correct? So now I compare gamma to alpha to see how well it's doing, right? Because this is what was really sent. Good so far? The question is, how do I capture its error or its performance? There's two ways to do that, right? I need to compare this to that, but in what way? The two ways to do this is, one of them is the word error rate. You basically see how many of these I got right. Meaning, anytime you have any error in the bits, that's a strike. So if I send 100 vectors, I see how many were not recovered correctly, right? And M is the number of channel inputs that are recovered incorrectly. N is the total. That's the word error rate. Now, realize in this case, I would count a guy as an error if one of the bits were not recovered, or 3. Doesn't matter. Anytime I don't get it perfectly, it's an error. What do you think is the other way of doing this? The bitwise, exactly. I basically count how many bits I sent total, and then I count how many were not recovered, and then compute the bit error rate. Now, this thing here is interesting. Look, here's an example. Let's say these were images, right? and every vector is capturing an image. So look at two situations. One in which I send 100 images. Every image has an error, but very small number of bits. And you're looking at it as an individual. You're okay. You're going to still recover the person's image, right? Even though they're 100% word error rate. Every image that was sent was not recovered perfectly, right? Versus looking at it from the point of bit error rate. So it depends on what you're optimizing, which one you would choose, the map versus the posterior marginal. And the posterior marginal is actually directed towards minimizing the bit error rate, which would be the right thing in certain applications. Let me mention one more point about this example before we move on, which again actually can be used beyond this example. And that's how to handle the noise model, right? So far we said, I send a bit, it's a 0, there's a probability of 1% it will show up as a 1, or generally to flip from 0 to 1 or 1 to 0. Now we're going to assume that, no, we have a Gaussian noise. So I give you a 0 bit, I send it, and effectively when you get at the other end is governed by a Gaussian distribution whose mean is 0, and that has a particular standard deviation. So in this case, the channel output is a continuous variable, right? It's no longer discrete 0 and 1. It's a continuous variable. Minus infinity to infinity, and it is a Gaussian that's centered on 0. And same thing for the 1 bit. If I send the 1 bit, I'm going to assume that it's governed by a Gaussian that is, mean is 1, and it has its own standard deviation. Now the question is like, how are we going to do this? We did not handle continuous variables in Bayesian networks so far, correct? Interestingly enough, you could handle this without adding continuous variables to the Bayesian network by simply looking at the evidence. What's the evidence here? Is a number, real number, right? By taking it and converting it to soft evidence using a base factor on either the 0 or 1. And it actually works out beautifully in this case. So let's assume that, I'll show you the equations, the derivations in the book. So the channel output is y, continuous variable governed by this conditional density. That's the Gaussian equation effectively. And there are, three variables here. The mean, x, that could be a 0 or 1, and what I'm seeing, the evidence, and then the standard deviation. It turns out that if you have this, you can implement it as, if you have a channel output, small y, that can be implemented as soft evidence on the channel input with a base factor of this quantity. The derivation is in your book, right? So, for example, you come and say, okay, the standard deviation here is half, and I received an output of 0.1. You can interpret this as soft evidence on this with a base factor of k around 5 by just plugging in numbers in that guy. And then you know how to do this, right? To incorporate this in a Bayesian network. You add a sensor, you pick up its false positive and false negative rates that correspond to this, and you will basically have the same effect. We're good? More details in the book, but we've seen this before, right? That you need this ratio to be 5, and then you can pick up a CPT for that, as long as it has the right false positive and negative rates. In this case, here are two different CPTs that will do the same thing. Again, here's this guy, and we just added this sensor, and then populated it by these numbers to emulate evidence on a continuous variable. We're good? You'll find this useful beyond this particular application. There are more interesting coding schemes that come up. So I'll just mention a couple of quickly to show you the network structure. You can read, the book has, all kind of details about these. One of them is called Convolutional Codes. and they look like this. Okay, these are the circuits. You see the details in the book. What I want to show you is this picture. What's happening here is, look what's going on. There is the information bits, the U1 through U4 as before, but now the redundant bits are generated a little bit differently. These guys are the S's, and you can think of it as there is a notion of state and time, where this redundant bit is a function of the previous one and the previous bit that I'm trying to send, and so on. What does this remind you of? Dynamic Bayesian network, right? This is basically, you can see the exact equations for how do I compute the S states in your book, but otherwise, the point here is that you have this kind of a structure. Let me make one more observation about this before I tell you about the other guy. This is what we call also, and we will dwell more on this when we do inference next, singly connected network. Singly connected network as opposed to multiply connected network. There are no loops, right? It's like a tree structure, except that a tree in which some nodes can have multiple parents. Like this guy has 2 parents, right? These are also known as polytrees, as opposed to trees. Trees, a node have at most 1 parent. Polytrees, they could have multiple parents, but still polytrees because you still have no cycles. They're also called sometimes singly connected. Now, why is that significant? Because as you'll see later, inference on networks that are polytrees is actually easy. Characterize the complexity. It's actually linear in the number of nodes and exponential only in the number of parents per node. Now, this is to be contrasted with the next and last type of codes that I'm going to show you, which I will make 2 points about. This is known as turbo codes. Okay, what happened here is we took 2 convolutional codes and put them together. In what way? Simply stated, if you look below, that's what we just saw, right? That's U0, 1, 2, 3, and that's the traditional convolutional code. Then what we did, we took these guys and permuted them, and then had another convolutional code for a permutation of that, and we just put them together, right? Now, why do you do that? What do you get? And all of that, that's, you need to go to information theory and coding theory and take a course in that subject. But from our point of view, I want to make basically the following key point, or 2 points here. One of them is, this is now no longer singly connected, or no longer a polytree. Now this is what we call a multiply connected network. There are loops now, right? And so it's more difficult to reason with these. But the thing I really want to say here and end up with is the following. Towards the late 90s, there was an influential paper that came out which made the following connection and almost basically started the whole field in approximate inference for probabilistic graphical model. So what is the connection? The connection is the following. On one end, in Yuda's original book from the 80s, he proposed an algorithm called the polytree algorithm, an algorithm that works on trees. It assumes that your model is a polytree, and then it works on it. It's an exact algorithm. It has the complexity that I told you. Linear in the number of variables, exponential only in the number of parents per variable. And then in one of the exercises in that chapter, he said, you could possibly use this even on multiply connected networks, but as an approximation scheme. And here's how you roughly do it. You basically iterate and do this and do that, right? And then in coding, when people do stuff like this, you have to come up with algorithms for decoding, right? So there was a turbo code algorithm that was popular and was viewed as a big thing in this area. And then people actually, in that paper in the late 90s, showed that if you take the coding problem and formulate it like we did here, and you look at the algorithm from coding that was being used for these guys, that ends up being Yuda's exercise suggestion, being that. And then it's like people, whoa, wait a minute. So that is actually not just an exercise, that's something. Utah's algorithm also was known as the belief propagation algorithm, the one on polytrees. So the approximate version was called loopy belief propagation or iterative belief propagation. And then that started the whole new thing about what's going on, because it turned out that that algorithm worked extremely well in certain cases. And there was tons of work on explaining what it was doing, how to extend it, when it works, when it doesn't work. Again, it was a subfield in approximate inference. We'll talk about this when we talk about approximate inference, because interesting enough, it's one of the simplest things to implement. You get a lot for a small investment when it comes to that algorithm. So I wanted to just end with that guy. Let's take our 10-minute break, and when we come back, we'll do a little bit more and then some more about CPTs and so on. 10-minute break.